Hi everyone! Today I'm going to be talking about how I trained an artificial intelligence agent to play a video game better than a human with deep convolutional Q learning. Deep convolutional Q learning is a reinforcement learning method. But what is reinforcement learning? Reinforcement learning is a subfield of artificial intelligence that is derived from human behavior, how humans learn and improve at a given task. Reinforcement learning trains an agent to be able to improve at a task in its environment through positive reinforcement or negative reinforcement, which is given from the environment to the agent in the form of reward. The agent and its environment first learns through exploration, then exploitation. The agent first interacts with its environment, identifies the current state it is in, and then takes action to move to a new state. After entering a new state, the agent receives either a positive reward or a penalty from its environment, depending how good the action was that the agent took in relation to the agent achieving its ultimate goal. This process then turns into a loop, allowing the agent to improve its actions every time it enters a new state by the environment giving the agent either a positive reinforcement or a negative reinforcement in the terms of rewards. Reinforcement learning is goal-oriented, the goal being to maximize long-term reward in order for the agent to learn through trial and error and output its desired task accurately. I trained my agent using the A3C algorithm, which stands for actor, critic, asynchronous, and advantage. The A3C algorithm utilizes deep convolutional Q learning at its core. So first, we have to understand what exactly that is. Basically, deep convolutional Q learning is Q learning, but with deep neural network. But what is Q learning? Q learning is a reinforcement learning method that uses the Bellman equation to update its Q value. The Q value determines the value of an agent moving to a certain state. The Bellman equation calculates the Q values of all possible states that the agent can move to next. So Q learning and the Bellman equation helps the agent identify which state and which action to take next in its environment. The only problem with the Bellman equation and Q learning is that it's only most effective with solving simple problems where there's only a limited amount of states. But when it gets to more complex situations, the Bellman equation in Q learning is not ideal. This is because we need to have a model which is able to have a performance as well as a human, and solve complicated tasks like a human. This means we need a model that mimics more human behavior. This is why, with deep convolutional Q learning, we are able to give our agent vision and the gift of sight. Deep convolutional Q learning gives the agent sight through convolutional layers. This gives the agent the same advantage as a human to perceive its environment and make decisions based off of that. The breakdown of how deep convolutional Q learning works is that the agent processes images that its environment supplies it, and it feeds these images forward through a convolutional neural network. Now, this convolutional neural network is made up of convolutional layers and pooling layers. And through this convolutional neural network, the images from the agent's environment are dissected. And they're dissected to identify the state that the agent's in and the state that the obstacles in the agent's environment are located. Now, the output of the convolutional neural network is numerical values of the state that the agent's in and the state that the obstacles in the agent's environment are located. Now, this is fed forward into an artificial neural network. So it's put into an input layer of an artificial neural network, and now the output of the artificial neural network is a vector of predicted Q values that detail the possible actions that the agent can take next. And now we choose the biggest Q value out of the predicted Q values out of the artificial neural network, and this will be the best possible action that the agent can take to maximize the amount of rewards it gets. However, in the beginning, our agent performs extremely poorly, and that is because the Q values outputted from the artificial neural network aren't optimized. And this is resulting because the weights of our artificial neural network aren't optimized. So in our case, we have to decrease the error by updating the weights of the artificial neural network, which results in a higher accuracy of the outputted Q values from the artificial neural network, which results in the agent maximizing the amount of rewards it can get from its environment. So we're able to calculate the error by taking the difference between the Q target, which is the maximum possible value of the next state, and then the Q value, which is our current prediction of the value of the next state. This right here is the equation for the error, which subtracts the Q target by the predicted Q value. The error or loss function is then backpropagated through the artificial neural network, updating the weights so that the neural network can now have a higher accuracy in outputting Q values that result in the agent gaining a positive reward from the environment. Now this is the part where the actor-critic part of the A3C algorithm comes into play. So basically the actor-critic is like the brain of the A3C algorithm, and at its core, it implements deep convolutional Q learning. But the only difference is that the artificial neural network, a part of the deep convolutional Q learning model, now outputs two sections, the actor and the critic. So basically the actor is the Q values. So the actor is the action probabilities that the agent can take. But the critic is V values. So the critic basically optimizes the actor. So it criticizes and judges how well and how accurate that the predicted Q values that the actor outputs are. Now the second part of the A3C algorithm is asynchronous. So the asynchronous part leverages 3 agents instead of 1 to be exploring the same environment and maximizing the rewards it gets in the same environment. And the purpose of this is because these 3 agents can share their experience exploring the same environment with each other. And this is because each agent is initialized differently at different starting points within the same environment. Now all the information from each agent is fed through one global network, and the global network outputs predicted Q values for each individual agent, which then gets optimized by a central critic. Final A from A3C is advantage. Advantage is how the critic tells the actor if its Q values are good or bad, and it calculates the policy